Hello everybody, welcome back to Chapter 4, a rotational view of the atmosphere. Here we'll be looking at Part 3, which looks at potential vorticity. Namely, we'll be looking at trying to simplify the vorticity equation even further in order to understand the fundamental dynamics that this equation is describing. So consider initially that we have a homogeneous incompressible fluid with constant density. So rho is going to be a constant. From the continuity equation, it then follows that the time derivative of density is equal to 0 and that the density can be taken out of the divergence term on the right-hand side in order to obtain a simplified equation, which is simply that the divergence of the velocity field is equal to 0. Written out in component form, this means that di u di x plus di v di y is equal to minus di w di z. We now take the vorticity equation with purely the divergence term. Remember, this represents the large-scale terms in the vorticity equation. We're going to take this and we're going to apply the continuity equation that we derived previously in order to replace the horizontal divergence term with a minus di w di z. So the consequence of this then for purely horizontal flow, that is where there's no vertical velocity associated with the flow, is that you actually have conservation of absolute vorticity in following a fluid parcel along the horizontal. So this simplifies things quite dramatically then, and we can use this in order to understand how relative vorticity is changing as the fluid parcel moves to different locations along the planetary surface. Namely, consider a fluid parcel, for instance, that's sitting at the equator. If that fluid parcel then moves northwards, then you're going to observe an increase in the value of F, which must be compensated for by a decrease in the relative vorticity zeta. So using this type of technique, one can then use the barotropic vorticity equation in order to understand the dynamics then of a fluid parcel which moves in the meridional direction. So the basic statement here then is that absolute vorticity is conserved following horizontal motion in a homogeneous incompressible fluid. So let's try something a bit more general. This is a bit too simple for the type of dynamics that we're interested in looking at in the atmosphere. So again, we're going to assume a homogeneous incompressible fluid, that is with constant density, but here we're not going to assume that W is going to be 0. So we're going to retain the di W di Z term that appears on the right-hand side of the barotropic vorticity equation. We're going to approximate the vorticity by the geostrophic vorticity, which is simply obtained by differentiating the geostrophic wind relationship, and we're going to integrate this vertically then from Z1 to Z2. Here we're implying a mean layer absolute vorticity here, which is retained for the absolute vorticity term. For the derivative term, we then have W at Z2 minus W at Z1 over Z2 minus Z1. So taking this equation, then we're going to define a layer thickness, Z2 minus Z1, or alternatively a column height, here denoted with the variable h. And we're going to use the fact that the change in a fluid column is simply given by the compression and expansion of the vertical velocity at either end of the fluid column. That is, if you have an upward vertical velocity at the top of the fluid column, this will correspond to expansion of the fluid, and a downward vertical velocity at the top will correspond to compression of the fluid column. So you can notice the analog then between this material derivative of the h term and the vertical velocity on each side. So plugging that into the equation then allows us to eliminate all the w's and z's from the equation, and we instead obtain a simplified relationship between the absolute vorticity and the height of the fluid column. Rearranging these quantities then gives us the form shown below. If we then take this and use calculus of logarithms in order to bring the factor of 1 over absolute vorticity into the derivative and the factor of 1 over h into the derivative on the right-hand side, we can then obtain a simplified formula, shown here at the bottom right, which simply says that this quantity within the square brackets will be conserved following a fluid. Now you'll notice that this actually reduces to the barotropic vorticity equation that we had derived earlier for W equals 0 in the case that the fluid column height h is constant. Now this makes sense because if you have no change in horizontal velocities in the horizontal direction, if you have no change in vertical velocity if you have zero vertical velocity in the horizontal direction, then h will be constant following the fluid flow. So hence we have for a barotropic, incompressible, and homogeneous fluid that the quantity within the square brackets is conserved following the fluid. And this quantity is a special quantity. In particular, it's known as the barotropic potential vorticity of a fluid column, and defined as PV and referred to as PV, which is equal to the geostrophic vorticity plus the planetary vorticity, all divided by the height of the fluid column. So the basic statement that we have then from the vorticity equation is that barotropic potential vorticity is conserved following a fluid column and measures the absolute vorticity relative to the depth of the vortex. So this quantity can be used very simply then in order to answer the question, what happens when a vortex moves over topography, assuming that the top of the fluid column is kept at a constant height? So here we have a fluid column which has a certain relative vorticity associated with it, or angular momentum or angular velocity, and as it transitions, it starts moving upward along topography and over a hill. This might be observed, for instance, for a fluid column transitioning up and above the Rocky Mountains, for instance. From our explanation using the barotropic vorticity equation, we must conclude then that there must be some sort of change in the properties of the fluid parcel which adjust for the fact that the height of the fluid parcel has changed. So recall that potential vorticity, which is zeta g plus f over h, will be constant following that fluid column. So if the height of the fluid column decreases, there must be a corresponding decrease in zeta g in order to ensure that the whole ratio is kept constant. Note that if we're at a constant latitude, the planetary vorticity term, F, will not actually change following the fluid column. And so the change must purely be due to the relative vorticity term. All right, so potential vorticity provides a link then between the depth of the fluid column and vorticity. As the depth of the vortex changes, the relative vorticity has to change in order to conserve potential vorticity. So this has a tendency to then link the rotational component of the wind, which is responsible for rotation in the horizontal plane, and the irrotational component, which, if you recall from earlier lectures, is associated with divergence or convergence of air into the fluid column, and hence adjustments in the height of the fluid column. So potential vorticity then indicates that there's this interplay between relative and planetary vorticity through conservation of absolute angular momentum. And it will be a very important quantity for understanding how fluid columns move in the presence of underlying topography. So recall that so far in understanding vorticity, we've built up this knowledge of relative vorticity and planetary vorticity. Relative vorticity occurring on the Earth's surface, and planetary vorticity just due to the rotation of the Earth itself. From that, we derived the vorticity equation, which has a number of terms associated with it due to advection, divergence, tilting, and baroclinicity. And we were able to eliminate several of these terms by noting that they were relatively small in comparison to larger terms. From scale analysis, we also found that the Rossby number is typically on the order of 0.1, which implies that relative vorticity is typically much smaller than planetary vorticity. So taking this fact into consideration, in addition to potential vorticity, then allows us to draw certain conclusions. In particular, observe that planetary vorticity is typically cyclonic or associated with positive vorticity in the northern hemisphere, and that planetary vorticity in the mid-latitudes is usually much larger than relative vorticity. Hence, a growing cyclone, that is a low-pressure system, which is growing, typically adds to planetary vorticity, leading to more intense lows, whereas a growing anticyclone will typically oppose planetary vorticity. That is, it tends to be subtractive from the planetary vorticity itself, and hence tends to lead to weak, high-pressure systems. So for potential vorticity conservation then, if we have a fluid column simply moving through a particular fluid regime, stretching and shrinking of the column will change the relative vorticity associated with the fluid column, And the use of constant density here is important in order to draw the conclusion that fluid does not change, that the fluid cannot be shrunk or expanded due to compressibility effects.